Hello everybody, welcome to Exponential Models. Today we are going to do the following. We are going to use the compound interest formula to solve real-world problems. We are going to use the continuous compound interest formula to solve real-world problems. And we are going to find exponential models using 2 consecutive points and exponential regression. Alright, so let's start with the first one. So first we're going to use the compound interest formula to solve real-world problems. So first of all, what is compound interest? So let's start off with the problem, and we'll kind of explain it as we go through the problem. So, in 2021, the population of a small town was 8,000. The population is increasing at a rate of 2.5% per year. Rewrite the exponential growth function to find the monthly growth rate. All right, so first of all, we already know what exponential growth is. We talked about this in the last lesson. Exponential growth is defined by the formula a of t equals a times the quantity 1 plus r to the t. All right, we're going to go and just put in the numbers that we found up here, right? Our initial population, which is a, it said was 8,000. So we're going to substitute in 8,000 for a here. And then for our r, we said that our rate was 2.5% per year, which is going to convert to 0.025. So that's our annual growth rate. And then t is the number of years after 2021, because that's what it said is 2021 was our initial. So this would be our growth rate, right? Just based on the year. So in other words, if we said, hey, in 1 year, how much will we have, right? We could substitute in t for 1, and we could figure that out. If we wanted to know 20 years from now, we could substitute in 20 for t and do that. But what they want to know specifically this time is what our monthly growth rate is, all right? So we only know how to find things so far in terms of time and years, right? So we need to be able to find it in terms of monthly growth rate. So I'm going to do a few steps here. I'm going to kind of explain the process as I went through it here. So the first thing we're going to do is when we know that we need to find the monthly growth rate, well, what that means is that every month we are taking that interest and compounding it, right? In other words, we're taking a value and then we're applying an interest rate every single month as opposed to every single year. And what that means is that our growth is actually going to be larger, right? Because we're going to gain money on the interest on top of gaining money on our initial investment. So it's actually, the more that you compound, the more money you make, the quicker you make money. So the first thing we're going to do is we're going to take this t, right? Normally this would be 1 times t, if you want to look at it that way, right? If we take this, it would be 1 times t. So what we're going to do is we're going to turn our 1 into 12 over 12. Because we know that really what we're trying to do is figure out how much 1 month gets us, and we know that we know that there's 12 months in a year. So we're going to take this 1 and we're going to turn it into 12 over 12, which doesn't change the value of it. It just rewrites it in a form that we can use. All right, now what we're going to do is this is the same thing. If you remember the power of a power rule, this 12 over 12, we can actually rewrite this as 1 over 12 times 12 over 1 as far as our exponents go. So what this does is this will move the 1/12 to be multiplied by everything that's inside our rate here, right? And then we'll also have this 12t on the outside. So in other words, this is saying is if we do this 1 out of the 12 times for the year, right? Because the total year was 12 out of 12. If we just take this rate 1/12 of the time, right? That's going to give us our increase per month. And then if we do that, of course, 12 times, we'll get the entire year. So really, we didn't change any of the formula at all. We didn't change the math behind it. We just rewrote it in such a way that now we can figure out what the interest rate is per month instead of having the total for the entire year, right? So if we take this if we take this 0.025 and raise it to the power of 1 over 12, and then add 1, we're going to get the 1.00206, right? And it's asking us what's our monthly growth rate. Well, our monthly growth rate is going to be the amount that we actually increased here, which if you move the decimal point over 2 is 0.206%. So this is our monthly growth rate, right? And of course, this changes the formula a little bit, but now if we did this 12 times, we'd be able to find out what we made for the whole year if we compounded monthly as opposed to if we just compounded the 1 time at the end of the year, okay? Now, I know what you're thinking. I don't want to do this every single time I have a math problem and it asks me to compound at a rate less than 1 year, right? That would be kind of annoying to do. So I went ahead and wrote out this formula for you this isn't my formula. This is a formula that's been known forever. But this is the formula for compound interest. All right. So we have A equals P times the quantity 1 plus R over N to the power of N times T. Okay. And if you look up here, it's the same thing that we did, right? We broke the N up into being multiplied by the T and being over our rate, which in this case would just be this, right? You'll see how it works out. So if we have A, right, which is our total value after T years, so we're still evaluating based on how many years, right? But in this case, we're breaking it down even more, right? The total value after T years is what our total is going to be, right? This is like the amount of money in the account after so many years. P is our initial value, so how much did we start with in the account? R is the annual interest rate. So in other words, how much are we making each year, or what is the interest rate every year? N is the number of compounding periods. In other words, this time, right, if we go up here, it specifically asked us for our monthly growth rate. That's why we divided this into 12, right? If it asked us for our biannual growth rate, right, that would mean that we would be looking at for it every 6 months. So we would do 1 over 2, right? Or quarterly would be 1 over 3, because you would do that 4 times, right? Or every 4 months, or you do it 4 times, so it'd be 1 over 3, because you do it, every 3 months, right? Okay. So, and then N would be the number of compounding periods, T would be the number of years, all right? So let's just try and do a problem, okay? Because honestly, what you're going to be doing is kind of plugging the stuff into the formula I just gave you, right? So here, I'll kind of talk you through it, and then I'll pause the video and see if we can figure this out, right? So 3,000 is invested into an account that earns 3% annual interest, compounded quarterly, right? So we're going to compound it 4 times. I'll help you with that, right? The N is going to be 4, right? Because we're compounding 4 times. What is the value of the account after 10 years? What is the effective annual interest of the account? Okay. So I'll go ahead and pause the video real quick, or go ahead and pause the video and give this a shot. At the very least, write out the formula, right? And then I'll have the calculator stuff ready for you. So, all right. Well, let's go ahead and jump into it then. So $3,000 is invested in an account that earns 3% annual interest compounded quarterly. What is the value of the account after 10 years? What is the effective annual interest on the account? Okay, so let's go and do this. So we have $3,000 is going to be what? Our initial investment, right? So we don't 100% off the top of this know we don't know the total yet. So we're going to say A equals 3,000 times 1 plus R, right? R is our annual interest rate, right? So R is 3%, which is 0.03 over, well, we're compounded quarterly, so that's 4 is our N, times N, right, which we just said is 4. I don't know why I put N. 4. And then this is T, so this is after 10 years, right? So we want to do 10. Okay, nice. So what we can do now is just kind of plug this into the calculator. If we go to Desmos here, I pulled this up here. So this is the equation up here, 3,000 times 1 times the quantity 1 plus 0.03 over 4 times 40, right? I just did the 40 because that's what 4 times 10 is. And I got 4,045 and what, 5 cents essentially. So we got $4,045.05. And that's going to be what is the value of the account after 10 years, right? So this is how much we'll have after 10 years, which means in 10 years, with just interest, we made about, what was that, 40,000? Let's say 40, 45? Okay, yeah. So we made around $1,045, roughly, right? Not too bad. What is the effective annual interest on the account? So in other words, like before we take into account of this here, we want to know like what is the effective annual interest? Like how much are we earning? Well, if we did this every year for 10 years, right, we would just want to know how much we were getting each year effectively, right? So there's a couple ways you could look at this. You could look at this as like, what is this? What is the number divided, right? So we'd have 1045.05 divided by 10, and that would give you like your yearly interest, right? The other thing you could do is just assume that this number here, this 10, is a 1, right? And then you could multiply this out with and this would actually give you the interest after 1 year, right? If you're still compounding quarterly, which is actually the way you should do it, right? So if I go back here to Desmos and I change this 40 just to a 4, right? I get 3,091 and 1 cent. So 3,091 and 1 cent, right? And this is what the annual interest would be after the first year, right? So you could keep doing that each time, right? But essentially, the average that you're going to get is going to be based on this number, and this would be the interest rate after like a single year, right? If it's compounded quarterly. So this would be like quarterly. So 1 year, quarterly, and this one would be like the average interest, right, over 10, like so per 10 years. Okay, cool. So not too bad, right? You kind of just plug the stuff in and then yeah, kind of put it into your calculator. It's really not too bad. Now they can ask you for things other than A, right? They could ask you for R or N or T. They can ask you for all that stuff. You don't necessarily have the tools yet to be able to solve all of those things. We will get into those when we get to logarithms, though. So for now, just kind of, solve for A, that sort of thing. Solve for whatever it asks for. And yeah, later on we'll be doing it in a little bit more complicated way. All right, so continuous compound interest. So before, what we were doing is we weren't compounding continuously. We were compounding a specific amount, right? In this case, we compounded yearly, and then we decided to compound monthly up here, right? And then down here, we compounded quarterly. But you notice how there's a specific number of compounds, right? Well, what this is going to be is when we compound continuously, it's as if we are effectively compounding an infinite number of times. We're compounding, like every moment we're compounding, right? That's kind of the idea behind this. So what if a bank account had $1? So in other words, your initial investment was $1, right? A yearly interest rate of 100%. So every year you kind of doubled your money, I guess. And compounded an infinite number of times in 1 year. So in other words, we're just making everything 1. We're going to try to make all these numbers 1 just so that we can evaluate n, right? And what we really want to evaluate is we want to evaluate n as it approaches infinity. Because we're actually, remember, n is the number of times we're compounding, right? If we go back to this formula down here, n is the number of times, the number of compounding periods. We don't have a number. It's infinity. We're literally trying to compound all the time, right? So as n approaches infinity, we can start to get a number for what this would have to be, right? So let's go ahead and go back into Desmos, and you'll see here, right? If we click on this, if we do this one, all right, so here on this formula, we have 1 plus 1 over n to the n, right? And then this would be times t, but t is just 1, so I got rid of the t, right? What we're going to do is I'm just going to show you, we want to look at this number here, right? We have 2.59. I put in n equals 10, right? And we have 2.59. So let's go back here, and where it says n equals 10, we got 2.59. Okay. Let's just do 3.7. Let's do the 4 digits, because this is okay. Because we're compounding so much, you want to be pretty accurate, right? So let's say what happens when n equals 100, right? So let's just take this 10, turn it into 100, and now we have 2.7048. So 2.7048. And you'll notice that n keeps getting bigger, right? And the reason why we're trying to make n bigger and bigger is because we want n to get as close to infinity as possible. Now, obviously, we can't do that, but what we're going to do is we're going to kind of hyper-exaggerate what happens when it grows from a very small number to a very large number, and then use that as a pattern, right? This is actually something you do a ton of in calculus. So we're actually kind of doing something that you'll get into next year a lot more. So now we're going to see what happens if n is 1,000,000, right? We did 10, we did 100. Let's see what happens when n is 1,000,000. 1, 2, 3, 4, 5, 6. Perfect. All right, so now it is a million, and we have 2.7182. So 2.718, we'll say 3 around that. 2.7183. Okay, so what we just figured out, right? The point of this is that if we take this here, this rate, right, where the rate is 1, and we compound continuously, we've determined that essentially what this is this is a base given a rate of 1, right, which the rate isn't always going to be 1, and we'll account for that in the formula below here. I'll show you in a second. But assuming that the rate is 1, this here will always approach, as n approaches infinity, will approach this number here, which is 2.7182. And what's really cool, if you're a person who loves history, right, and you also love math, I would look up this number and all of the implication that this has on the real world. It's actually crazy how often it comes up, and it's really interesting. It has to do with this 1 over n concept here, 1 plus 1 over n concept. There's tons of stuff that ranges from looking at prime numbers. There's so many things that happen in the real world that are associated with this number. So if you want to look up Euler's number, it's actually really cool. But in math, we define this as the letter E. So we're going to look at this as the letter E, and that equals 2.7182 approximately. A lot of calculators have E. It'll say like E to the x, right? Because you're almost always using E as a base for an exponential function. So let's go ahead and look at our new formula, right? So this is our compounding continuously formula. It's a little bit different than our interest formula. I'll go ahead and pull it side by side so you can kind of see the similarities and the differences. All right. So A equals PE to the power RT. We call this PERT, right? You'll hear people say that. So A is the total value after t years. That's not changing, right? A is our total amount that we're going to have. P is our initial value, exactly the same. R is our annual interest rate, which is exactly the same it was before. And T is the number of years, right? So it's actually easier because we have a consistent amount of growth. The formula is actually a little bit easier to use. So we're going to use this, P equals ERT. And I want you guys to pause the video. I want you guys to use this formula that we just did. I want you guys to give this a shot. I know we didn't do one together, but we did one with compound interest, right, where it's not continuous, and it's very similar. So I think you'll be fine. Go ahead and give this a shot, and then we'll come back together and we'll try it out. All right, welcome back. Let's go and give it a shot. So Regina invests $12,600 in an account that is compounded continuously. What is the value of the account after 12 years, rounded to the nearest dollar, if the annual interest rate is 3.2%? All right, well, we're going to use our formula we just did, right, or we just learned. So this is PERT. Right, well, it's A equals that, right? Here, all right, so yeah, A equals P E to the power RT. Okay. So she invests $12,600. That's going to be our initial investment. So we know this is $12,600. And then E, which is, like I said, this is just a number, right? Think of it kind of like pi. It's an irrational number, right? And this is all going to be raised to the RT power. So 3.2 is 0.32. 0.032, right? And then raised to the t, which is time, 12 years. That's it. So now it's just a matter of plugging it into your calculator, right? So if you plug that one into your calculator, you will get, here we go, here's the number. All right, so if we plug this in, we get approximately, right, and it's asking us rounded to the nearest dollar, so we can just say equals $18,498.63. So $18,499. And this is rounded to the nearest dollar, as it asked us to do. All right, not too bad, right? Just kind of plugging stuff into the formula. All right. Now let's look at a concept this is maybe a little bit trickier, right? This is us being able to find these equations and these functions with given limited information. So let's see what we can do here. All right, so now what we're going to be doing is the final part, which is finding exponential models using 2 consecutive points and exponential regression. So let's go and give it a shot. All right, finding exponential models. So let's start off with a problem. Tia knew the number of instant messages she sent out was growing exponentially. She generated a record of the number of instant messages she sent each year since 2018. If in 2022 she sent 6,000 instant messages, and in 2023 she sent 6,600 messages, what is the function which describes this data? Now, first thing to understand is any exponential function is going to be written in this form here, right? Y equals a times b to the x, right? That's actually all these other formulas are, right? They're just a little bit more broken down. This is a times b to the x, right? There's just a t there and an r, right? These are all the same. It's the same idea, right? A is our initial value. B is our ratio that we're using to multiply our rates and all of that stuff. So if we look at this, we have, well, first of all, we have to define our x and y's, right? So y is going to be the total number of messages in the hundreds, right? So in other words, 6,000 here, 6,600 here. That's going to be our total number of messages. So we're going to use that as y, right? And we use that as like a of t in the past. It's a, it's right over here. It's a equals p equal rt, right? Over here, it's a equals this, right? This is our a in this case, which is y. Okay, and then x is the number of years since 2018. So in other words, if it was 2019, x would be 1, right? It's the amount of years going forward. All right, now, like I said, a is going to be our initial value. This is always what we're looking for as far as like where's our starting point. And then b is going to be the scale factor of growth, and this is going to be in the form of a ratio. In this case, I mean, all these numbers are irrational numbers. Irrational numbers are just ratios that don't divide evenly, right? So makes sense. All right, so the first thing we notice is that we have a couple of points then, right? Because if we know that x is the total number of instant messages in the hundreds, or if that's y, and then x is the number of years since 2018, we actually have 2 sets of points, right? Because up here it says, if in 2022 she sent 6,000 instant messages, right? Well, 2022 is 4 years after 2018, so that's how we get this point down here of 40, 6, or 4, 60, right? The 60 being this, in hundreds, so there's 60 hundreds here, right? So we divide this up. So 40, 60. You could leave this as 6,000 if you wanted to. I just like to make the numbers smaller, right? There's no reason not to, in my opinion. And then over here, we have in 2023, she sent 6,600, right? So here, this is going to be 5 years, which is the year after, and then 6,600s, right? Okay, now, the important takeaway from all of this is that you'll notice how this is a point of 4, 60 and then 5, 66, right? These are consecutive points. The only way you can do this without learning how to do logarithms is to do this with consecutive points, okay? So we'll talk about it when the points are not consecutive later, but essentially what you're going to do when they're consecutive is you're just going to find the ratio by using y sub 2 over y sub 1, right? In this case, y sub 2 was 66, y sub 1 was 60, so we can just kind of divide those two by each other. 66 divided by 60 is 1.1, right? So this is the ratio we were looking for, and that's what we can use for b, right? So now in order to find a, right, if I go back up to my initial formula, if I know b, right, I know an x and a y value, right, because we have 2 points here. So I can plug in a point for x and y, and that'll give me the ability to solve for a, and that's what we're going to do. So to find a, use one of the points from above. I chose the 66, 5, 66 point. It doesn't really matter which one you choose. So 66, which was y, equals a times 1.1. And remember, that's b. That's what we just found, right? To the 5th power. And then this is 66 over 1.1 to the 5th. We just kind of divide both sides by this whole expression here, right? And then if you finish that off, you're going to get 40.98, right? And what 40.98 is that's our a. So now we have our a and our b. We can rewrite this as our rule, right? Or as our, if you want to, this is our model. This is our rule for our equation here. So we have y equals 40.98, which was our A, times 1.1, which is our B, to the x, right? And this is the function that models all of the data that Tia recorded. Sorry, wrong problem. Perfect. All right, that's it. I mean, if you have 2 points, you set them up as a ratio against each other, essentially, and that solves for B. And then once you have B, you kind of plug in one of those points to solve for A. All right, so what if we don't have consecutive points, but we have quite a bit of data? Well, in that case, we can actually use our calculator to help us out quite a bit. So what we're going to do in this case is what is known as exponential regression, and this gets pretty technical on a step-by-step basis. So just kind of follow along on this one, okay? I don't think there's, if you want to try another problem, there are problems I can give you. There are also problems in your packet. But as far as this goes, just kind of tag along here for a second. So a radioactive iodine isotope that decays over time is used for medical treatments. A hospital pharmacy must keep a backup supply. When there is 40 milliliters of the isotope, the pharmacy orders a new supply. Find a model for the amount of iodine isotope after X days. Should the pharmacy reorder a new supply before the 12th day? Okay. So, basically, our hospital keeps a certain amount of this isotope, right? This iodine isotope. And every day they use so much, right? And the amount that they use is not linear, it's exponential, right? So, and I'm not sure why that is, but that's the way it works, right? So what they want to know is, how can we graph this, right? How can we graph it? How can we find our A and our B, just like we did in the last problem, right? We need to know the rule, right? This isn't a rule, this is just a set of points, right? So how can we use the set of points to define a rule? Because you'll notice none of these points are consecutive, right? We go from 0 to 5 to 10. We can't just do what we did above, and we don't know logarithms, so we don't have that in our pocket yet, right? So how can we use our calculator to help us? Well, I kind of did a step-by-step thing here, and I'm going to do the step-by-step thing, and I'm going to show you on Desmos what I did, okay? And then hopefully this will help you out. So what we did is, first of all, we have this chart that lists, okay, at day 0, we had 120 milliliters of our iodine isotope, right? And then at 25 days, we only had 12.8, right? Which would be that's not enough. We would have to have ordered it before then. We're trying to find out at 12 days, should we have already ordered it, right? Because we have to have at least 40 on hand. Okay, so let's go to Desmos, right? Now, I gave you a step-by-step guide here, right? And we're going to be talking about this guy here. Okay, like this thing. We could probably get rid of this. It doesn't matter. Okay. So we're looking at x sub 1, y sub 1, right? And it's important that we label these accurately, so that way when we actually go to do what we're about to do, that we have the right thing, we have it in place, right? So first thing you're going to do is click on the plus at the top left and select table. So what I did is I clicked here and I went to table, and that popped this up, and it automatically generates x sub 1, y sub 1, right? I'm going to just erase that just to kind of show you. But yeah, and then what I did is for x sub 1, I filled in the list. This is our x values are the days, right? And then our y value is the number of milliliters. So that's what I did. I plugged in my x and my y. Like I said, ignore this e thing. That's just more for my fun. So we did the x and the y, right? Perfect. So now we have our chart, right? That's enough to like plot these green points, right? If I shut this off, you'll see that like, if you look at the points, right, you can kind of see what's going on, at least from the points perspective, all right? Okay, so now we go back here. Input the data. Okay, that's what we did. And a new box, type this. And this is, it looks a little strange, right? But it's y sub 1, and then it's the sign for similarity. I think it's called a tilde. Y sub 1, and then this tilde. And then AB to the power of x sub 1, right? And if you think about this, this kind of looks like a formula. This looks like our typical formula, right? Y equals AB to the x, right? So this kind of looks like this. And then you want to check this log mode button, okay? Make sure you check this, all right? And now what you're going to do, I mean, you don't have to click on this button, but this button will automatically populate, and this will show you the graph, right? And you'll notice on here, right, this is specifically what we're looking for, this A value and this B value, because these are what we can use to generate our rule, right? And that's just the answer, right? So if we go back up here, right, check the log mode box, cool, we did that, right? Log mode, sounds good. So y equals and all I did was plug in my x or my a and my b, right? A equals 122.33, right? 122.33 right here. And then b equals 0.92, right? 0.92. Awesome. And so our actual formula is y equals 122.33 times 0.92 to the x, right? This is our rule. So the question is at x equals 12, what is y, right? Because that's what we need to know. Like when x is 12, do we have at least 40? That's what we need, right? We always need 40 on hand. So if we go to x and we want to know, do we have 40, or where x is 12, at 12 we have 42.72, right? Which is, yeah, I mean, I kind of rounded it a little bit. But yeah, so 42.73, right? So do we have 40? Yes, we do. So we don't need to order quite yet, right? It's probably close, like it's probably day 13, right? That we're going to order it. But as of day 12, we're good, right? Just by a little bit, but we're good. All right, now this is an important takeaway, okay? I showed you how to do this on Desmos. There may be tests you take in the future where you don't have access to Desmos, right? I would strongly recommend going on Google, typing in the name of your calculator, and then typing in regression, right? Exponential regression. And it'll take you step by step through. If you want me to help you with that, I'd absolutely be happy to do that, okay? But I strongly encourage you to familiarize yourself with that process on your specific calculator, okay? All right. Well, as far as the concepts for this lesson go, that's just about it. So first of all, we started off by kind of very quickly reviewing exponential growth and then going into compound interest, right? Compound interest formula and all that stuff where we compound a specific number of times. And then we went into continuous compound interest where we talked about Euler's number, which is E, right? And this is a new base that we can raise everything to for compounding continuously. And then we talked about finding exponential models. In other words, finding the rule, setting up the formula for y equals a times b to the x, right? And we did that for if we have consecutive points without using a calculator, and then we used exponential regression on a calculator to help us when we have multiple points. And obviously, the more data we have, the more accurate this is going to be, because the exponential regression model is essentially it's an estimation, right? It's an algorithm. It's a projected estimation, right? So it's doing its best, and the more points you have and the more points you give it, the more accurate it'll be. So, all right, awesome. Well, that's everything for this lesson, and I will see you in the next video.